Near the township of Ettalong, the northeast arm of Broken Bay winds inland. Behind the headlands, it threads its way north to spread wide and clear as far as Gosford. This vast waterway, known as Brisbane Water, washes the western shore of a giant peninsula, stretching from Gosford to the Pacific Ocean. With the increasing development of this part of the central coast of New South Wales, a bridge was required to provide a link between the relatively isolated eastern side of Brisbane Water and the rail and road facilities of the western side. The site selected is known as the Rip, where the waters narrow to a channel about 200 meters wide. The narrowness of the channel creates high flows of water with the movement of the tides. Because of these rapid currents, the construction of the bridge foundations in the form of piers in the channel was undesirable. It was decided to construct an arch-shaped bridge of very high-strength pre-stressed concrete, cantilevered across the channel to avoid the need for permanent piers or temporary supports in the strong tidal flow. The bridge comprises two cantilever trusses, each 147 meters long, and a central suspended span 36 meters long. The overall length of the bridge is 330 meters, with a main span of 183 meters and a vertical navigational clearance of 50 meters over a width of 70 meters. Each cantilever truss is supported on a pier, which is founded on board piles in shallow water close to the shore and anchored to an abutment, which is also founded on board piles. A cantilever truss comprises 8 panels and many members, mostly precast and pre-stressed. In the 2nd to 7th panels, the bottom chord or arch rib and the top chord or deck are separated by columns and diagonal ties. The 1st and 8th panels are constructed of pre-stressed concrete girders of variable depth. With the abutment and pier complete, construction of a cantilever truss was commenced with the erection of the arch rib members of panel 4, one end being supported on a false-work tower. The first diagonal ties were constructed and 2 precast columns were erected. The panel was completed with the erection of the deck members, placing in situ concrete and pre-stressing. Similarly, panel 3 was constructed. Cantilever construction of panel 5 over the water followed, and pre-stress was applied. The weight of the overhanging panel was balanced by the panels previously constructed on the shore. Construction continued progressively, the shore span being always in advance of the span over the water, so that there was always enough weight in the shore span to more than balance the weight of the construction being cantilevered over the water. The shore span was anchored at the abutment, the temporary supports were removed, and the addition of panel 8 completed the construction of the cantilever truss. In September 1971, a contract for construction was awarded to John Holland Constructions Proprietary Limited. The many precast members for the bridge were manufactured at their casting yard in Seven Hills and at the EPM factory in Blacktown. Each of the precast members incorporated bearings, stressing anchorages and ducts. The largest of these were for the arch ribs and weighed over 50 tons. At the bridge site, the main pier was constructed. The base of the pier incorporated temporary bearings and a battery of Tracy flat jacks to support the lower end of the arch rib members. The flat jacks were partially inflated with oil and together with the temporary bearings would provide hinges for rotation of the arch rib members during construction. The arch rib members were transported by road to the bridge site. A powerful crane positioned each arch rib member with its lower end bearing on the base of the pier. The upper end of each member was supported on a falsework tower. Concrete was cast between the ends of the 5 precast members, joining them together to form a cross girder. High tensile steel cable was inserted in the ducts and pre-stress was applied. Two diagonal ties were then erected. Each tie member was cast in 2 halves, each of which was supported on erection bearings. Pre-stressing ducts were installed between the 2 halves. Cables were inserted, concrete poured, and pre-stress was applied. The end of the arch rib was now effectively tied to the top of the main pier. Concrete was placed between the flanges of the arch rib members, so combining them into a single cellular rib. 2 precast columns were erected and temporarily supported by strutting from the ties. The columns, like the arch ribs, were seated on temporary bearings. All temporary bearings were left unconcreted to permit hinge action during construction. The erection of pre-stressed concrete deck beams followed. These incorporated longitudinal ducts in which cables would be inserted to progressively pre-stress the whole deck. The deck beams, like the other members, were seated on temporary bearings. 5 deck beams were erected in this way. After placing of in situ concrete and pre-stressing transversely, longitudinal stressing tied the completed deck back to the pier headstock. A specially designed erection truss was mounted on top of the completed panel. Construction of the adjoining panels then proceeded. The erection truss now played the major role in handling and positioning the heavy precast members. Cantilever construction over the water commenced with the erection of the arch rib members of panel 5. Pre-stressing cables for the diagonal tie were anchored to the outer end of the arch rib member. The shore end was supported on the temporary bearing and flat jacks at the base of the pier. The outer end was supported by the pre-stressing cables from the pier headstock. The calculated deflection behavior of the cantilever truss during the course of construction was allowed for in the determining of all temporary erection levels. The external arch rib members were fitted with a temporary headstock. This temporary headstock supported the outer end of the remaining arch rib members. Construction of panel 5 continued and was more than balanced by the completion of panel 3. A further stage of pre-stressing through the deck tied the completed panels together. As construction of the cantilever truss progressed, additional stages of pre-stressing the deck were required to counteract the increasing loads on either end. panel 7, the arch rib members were suspended individually by temporary cables positioned to allow for the casting of a massive cross girder extending upwards to deck level. This cross girder and an identical cross girder in panel 2 served as anchor blocks for longitudinal pre-stressing and also tied the arch rib and deck together. Meanwhile, the truss was positioning the precast girder segments for panel 1. The first segments projected halfway between panel 2 and the abutment and were seated on erection bearings at their bases. An upper cable was used to hold each segment in position against the anchor block in the end of panel 2. With the segments for the first part of panel 1 in place, formwork was erected for the joints between the flanges and the transverse joint with panel 2. After concreting, this part of panel 1 was pre-stressed. The newly constructed cross girder at the end of panel 7 was pre-stressed transversely with cables. It was also stressed vertically with high tensile steel bars, thus providing anchorage to the arch rib. The cross girder was then ready to provide anchorage for the cables which would permanently support the panel 7 arch rib. The 5 temporary cables supporting the arch rib were augmented by 4 cables anchored to the top section of the cross girder. These were stressed to share the load with the 5 temporary cables. The 5 temporary cables could then be transferred, one at a time, from the arch rib to the cross girder. The whole changeover operation required a period of 3 days to complete and resulted in the arch rib of panel 7 being supported by the cables anchored to the top section of the cross girder. The additional weight of the panel 7 deck during construction would also be taken by these 9 cables. The deck levels were checked at key points along the cantilever truss. Observed discrepancies between actual and predicted levels were then corrected. This was achieved by the operation of the flat jacks in the open temporary joints at the pier base and at the ends of the arch rib members. At each joint, in turn, the flat jacks were connected in 2 hydraulic circuits. Oil was pumped in to inflate the jacks and open the joint. Correction to the shape of the whole structure was made possible by the hinge action of these joints and the other temporary joints in the deck and columns. This operation had the effect of raising the cantilever so that each key point was brought to the desired level. Subsequent deflection behavior of the cantilever truss was sufficiently predictable for the temporary hinge joints in the arch and deck to be fixed. Oil in the jacks was progressively displaced by grout and the joints concreted. Panel 1 was then completed by the erection of the remaining segments. These segments reached to the abutment, and after aligning, joints were concreted and the whole panel was pre-stressed back to the cross girder in panel 2. In panel 7, the deck was concreted in situ. The bottom slab was constructed first, and the ribs and top slab were formed using polystyrene void forms. Concrete was pumped from the shore. Additional cables were threaded through the length of the deck from panel 1 to panel 7 and stressed. Also, the cantilever truss was anchored at the falsework towers near the abutment. Free cantilever construction of panel 8 could then proceed with safety. This was attached in 2 parts in a manner similar to the construction of panel 1. With the completion of panel 8, the stage was approaching when this cantilever truss would be linked with the one constructed on the other shore by the insertion of the suspended span. Preceding this final major operation, fascia panels would attach to the arch rib. Cantilever panels were added and incorporated in the deck by the placement of concrete. Meanwhile, the erection truss was launched to bridge the remaining gap in preparation for the erection of the suspended span. For the launching operation, it was necessary to counterweight the partially dismantled truss and to provide a needle beam to receive it on the far side. Deck concreting was then completed through to panel 8. A further stage of pre-stressing was required to prepare for the placing of the suspended span girders. This stage of pre-stressing required cables approximately 150 meters long. All cables used in the bridge were manufactured on the site. The BBR system was used, and cables were made up of 55 7mm diameter high-tensile steel wires. This system requires the wires to be cut accurately to length and button heads formed on the ends. With such long cables, stressed to over 250 tons from both ends, the extension was as much as 600 millimeters. Because of their length, each of the girders for the suspended span was assembled from 4 precast segments. Each set of segments was aligned to a predetermined camber and the joints concreted. Pre-stress was applied to complete the girder. Before the girders were launched, roller bearings were installed at the end of panel 1, and each shore span was anchored permanently to the abutment by means of precast holding down beams and vertical high-tensile steel bars which were pre-stressed. The girders for the suspended span could then be launched. When disconnected from the launching truss, each girder was finally positioned by winching sideways on supporting skates. The eastern end of each suspended span girder was supported on a fixed bearing. The western end of each girder was supported on a stainless steel roller bearing. These bearings, together with those of the abutments, provided for the predicted longitudinal movement of the bridge. Following the final stage of pre-stressing the deck of the cantilever trusses, the deck of the suspended span was concreted. The lightweight, high-strength concrete used in the deck and girders of the suspended span reduced the weight of the suspended span by 20% compared with the weight of the normal high-strength concrete in the cantilever trusses. After concreting the temporary joints, the columns were pre-stressed and false work removed. Crash barriers were constructed on the deck, handrails and crash rails were erected. Precast slabs were laid for the footway, covering a services duct in the space below. Lamp standards were erected, and spray painting of the railings completed the contract work. Two kilometres of approach road, including a bridge over a local road, were constructed by the Gosford Shire Council. Finally, an asphaltic concrete surface 60 millimetres thick was laid on the bridge by the department's own labour and equipment. On Friday, the 14th of June, 1974, the bridge was opened with a ceremony at the western abutment. Many local residents were among the large gathering of guests addressed by the Commissioner for Main Roads, Mr. R.J.S. Thomas.
And today, the younger people of this generation, I think, are witnessing the opening of a bridge which is a milestone in New South Wales, a milestone in technology, and a milestone in beauty. And I'm sure that you will go away from this ceremony very much enriched by the message which the acting Premier, Sir Charles Cutler, who is our Minister, will bring to you this morning. And ladies and gentlemen, I have much pleasure in asking Sir Charles to address you.
Sir Charles Cutler, acting Premier of New South Wales and Minister for Highways, addressed the assembled guests.
Ladies and gentlemen.
Sir Charles complimented the department on the roads and bridges it was producing for New South Wales.
So, although I don't dedicate this particular bridge, I could very well dedicate bridges such as this and the beautiful roads that are being built by them to the men and the women of the Department of Main Roads who do a tremendous job for this state and for Australia. I pay tribute to them, and I have very much pleasure in declaring this bridge officially open.
The completion of the new bridge at the Rip, by providing a direct road link to the eastern side of Brisbane Water, will accelerate the development of this area of the Central Coast. The improved access will be shared by both residents and tourists alike. In this bridge, the design staff of the Department of Main Roads, with the advice of the department's consulting architect, has produced an advanced design of open cantilever concrete trussing. Weight was minimized by adopting hollow cellular structures for the top and bottom chord members. The arch shape of the bottom chords minimized the loads in the vertical and diagonal members and produced the generally slender appearance. Construction, following a strict predetermined sequence and involving many new and complicated features, made heavy demands on the skill of the contractor, John Holland Constructions Proprietary Limited, and the Department of Main Roads supervising staff.